Welcome back, class. Good to be with you. This is Whitlock and Schluter Chapter 12. The title is Comparing Two Means, and I'm going to break this up into three parts. We're going to focus on just the big picture stuff here in the first part. There are two broad categories of situations we're going to be talking about. And the first one is the two-sample case. So I'm going to depict it like this, with two different circles, two different populations going on here. So we're going to have population 1 and population 2. Now, they're going to have an unknown mean, could be another parameter, possibly a proportion. Both of them have a mean here in this case. And we take a sample from both. So I've got sample 1, and I will get sample mean 1, x bar 1, and sample 2. What we're interested in is there a difference between the first mean and the second mean? What's the relationship between those two? We can look at that question either through a confidence interval or a hypothesis test, and so I want to show both. But the key thing here is that the two populations are independent. So this is the independence case. Independent. They're taken separately. The sample sizes N1 need not be equal to N2, although they could be. The two groups are simply different, and what we're interested in is the mean of the first equal to the mean of the second. That's really what we're interested in. Now, by contrast, let's look at the paired case. Whitlock and Schluter use a different diagram. I'm going to put my diagram like this. There's a single population in the paired case, but we're taking two observations from it. So we're going to get a mean 1 and a mean 2 are inside of the population. But really, the way I like to think of it is that these two are there's some difference between the two. And so let's depict that with a single sample. And I'm going to have a x bar with a difference between the two means. Okay, so you'll take two observations and you will subtract them from one another. So you could think of that maybe an x and a y, but then we're going to subtract the two. X minus y is going to give me this difference. And it's those differences that I'm going to look at. This is the paired case. I think examples help to make things most clear. Let's see. If you have a paired case, then those two guys, your two groups, N1 and N2, they have to be equal to each other. So N1 equals N2, and you can say, is mean 1 equal to mean 2 or not, but I can also say, is the difference equal to 0? That's what we're really looking at. And so your x's and your y's can be plotted in a scatter plot. You always have the same in each group because they're paired. This observation here represents the measurement of x and y on whatever unit I'm measuring. For example, I've got a few out here. The performance of the spring biostatistics class compared to the fall biostats class as measured by final percentage grades. This one is clearly the independent case because the students in both classes are independent of one another. It's two different groups. Don't have to have the same sample size. I'm interested in whether the means are the same or not. How about this one? Is the freshman 15 a myth? The weight of freshmen on the first day of fall semester and the weight of the same freshman on the last day of the fall semester. That's paired. Because it's the same student. So I could do a plot. Maybe they start out light and get heavy. That's the freshman 15 line of thinking. Okay, but there's really one population that I'm drawing from. By contrast, this one is 2. This is all students that would take biostats in the first semester versus those who would take it in the second. Okay. Go ahead and take a shot at these next 4, and we'll discuss those in class. Now, I want to talk about interpretation of these if we do confidence intervals. All right, so in the confidence intervals context, what we would do is we would have 2 groups. So, for example, let's just let group 1 be the fall class, and they're going to come up with, let's say, sample mean 1 of 78%. Okay, and we'll let group 2 be the spring, and they're going to have X bar 2, which is, we'll say, 83%. Okay, now, question. From the population of students that would take biostats in the fall, do we expect that they have the same mean as those who would take biostats in the spring? Or let's suppose that I made some course changes. I did some things differently in the course. Or did the grades increase? They're independently measured. What we could do is we could measure a confidence interval on both. And so if we did that, then group 1 would be here at a 78, group 2 would be here at an 83. And let's just suppose that this was the confidence intervals. Notice that there's no overlap between the 2. And so what this would imply is there's a significant difference in the 2 populations. The innovation that I did resulted in a grade increase. By contrast, in this case, I have 78, 83. Notice that this bar goes all the way over here, and this 83 confidence interval contains the center of the 78 one. We can infer that the 2 means in the population, again, are not significantly different. Okay, this is just on the simple confidence intervals we've already learned. Now, in this case, I have my 2 groups, 78 sample mean, 83 sample mean. And you'll notice that the confidence intervals overlap, but they don't contain the center of the others. This one is unknown or ambiguous. So, what I'm asserting to you is a difference of means. Confidence interval can break the tie. Can break the tie. In the A case, the 2 means are significantly different. If we were to construct such a confidence interval, and I'm going to go ahead and just give us a baseline here. Well, let's confidence interval 83 minus 78, x bar 2 minus x bar 1 is 83 minus 78, which is 5. Okay, so a 5 is going to be the center. And let's just, let's do it up there. Case A, put the 5 right here. And let's suppose that it goes up to 8, down here to 2. The difference is somewhere between 2 and 8 percentage points at the 95% confidence level, let's say. Therefore, we infer that there is a real difference between the 2 groups. Okay, let's take the not significantly different case. We have the same center here of 5, but now maybe it's a wider interval. we go all the way up to 12, and down here to -2. Well, if this line is at 0, 0 would be the no difference case. This confidence interval includes either no difference, spring better, or fall better. That was case B. Let's do case C, the ambiguous case. What the ambiguous case can do is break the tie. It's ambiguous here. We could get something like, we'll say 1 to 9. And so the difference between the two means is from 1 to 9 percentage points at the 95% confidence level. It's all positive, therefore we infer that there is actually a difference. C is able to disambiguate. It may not always, this could slip over, but it can break that tie. And so what that shows us is the value in doing a new approach beyond treating each of these two populations as an individual population, all isolated, and then just comparing afterwards. If we compare before, then we can squeeze out some information, and I'll show that in the next presentation.